Hi, good afternoon to you all. Today we will be discussing assignment number 10 and sorry for changing the timing of the session this week from Friday to Sunday because I was unavailable on Friday, but this would only happen for this week only. The next week onwards we will be having the live sessions at Friday from 7 to 8 p.m. only. So today we'll be looking at assignment number 10. I'll be sharing my screen. I hope my screen is visible. So as told, we'll be discussing assignment number 10 and we'll be looking at some typical questions of this assignment. Of course, like the previous live sessions we used to have, this would be focused on the assignment from the previous run. And this assignment is based upon the symmetrical components and the fault MVA levels in power system. So let's start. So this is question number 1. A three-phase generator rated at 132 MVA, 13.2 kV is connected through circuit breakers to a transformer. The generator is having a direct axis subtransient reactance of 19%, transient reactance of 26%, and synchronous reactance of 130%. The generator is operating at no load and rated voltage when a three-phase short circuit fault occurs between the breakers in the transformer, then what would be the magnitude of the. So since we are dealing with a three-phase fault, so as we know, we have to consider the subtransient reactance, right? Because during faults, when the synchronous generator gets short circuited for let's say 2 or 3 cycles, for the first 2 cycles, maybe only the subtransient reactance or XD double dash is operable. So which is 0.19. Now our base is 132 MV and 13.2 kV. Now in a three-phase fault, we know that the fault current is the synchronous generator voltage divided by the synchronous reactance. So the your EG would be 1 here because we this is the base only. So I mean 13.2 kV is the base, and since there is no other system in the, so we'll consider EG as 1, right? So 1 divided by 0.19 per unit would be your fault current. Now this is in per unit, right? So we have to calculate the value of fault current in amperes. So we have these base components, and by the base divided by the voltage, we get the fault current, which is your 30.386 kiloampere, which is your option number B. So this was a pretty simple problem. Now let's go to question number 2. It states that in a power system with negligible resistance, the fault current at a point is 5 per unit. A series reactance which is inductive in nature of 0.8 power per unit is included at the fault point. Find the percentage change in the fault level. Means the fault current ka change we have to find. So the initial fault current was 5 per unit, right? And the initial reactance So yeah, so we have to calculate the initial reactance. Now for our reference, we have to assume that the voltage at the terminal point would be 1 per unit, right? So your fault reactance would be the voltage divided by current, which is 0.2. Now they are saying ki another series reactance. So reactance basically in series of 0.8 per unit was connected with the system. Therefore, the changed or the increased this thing, the reactance value would be what, zero point 0.2 plus zero point 0.8, which is your 1 per unit, right? And hence the changed fault current would be highly reduced, right? Because your voltage is constant, so 1 by 1 is 1 per unit. Now they are saying what would be the percentage change in the fault level. So the basically the change in fault current, right? So delta IF would be what, 4, and it has changed by 4 by 5 into 100, which is 80%, which is your option number C. This was also pretty simple problem. So we will be, these problems are very simple provided you know the formula, you know the know-how, how to do this, you know the concepts and all. Pretty simple problem. And 11 and 12 would also be simple. So probably 11 would be assignment 11 I'm talking about would be on faults in power systems, various kind of faults, and probably the last assignment 12 would be looking at the stability of synchronous generators. So these two topics are pretty simple, and they are also one of the most important topics of this power system analysis. Yeah. Okay. So these problems are simple. We will try to wrap up this assignment 10 in very quickly. So I'll be going through all the problems, and of course you will be, getting the video and also this PDF file. Also, I'll be uploading it shortly after the live session ends. So let's look at problem number 5. So two generators units G1 and G2 are connected by 15 kV line with a bus at a midpoint as shown in figure 5. So this is basically the system. So there are two generators G1 and G2 which is connected by this transmission lines. So there is this one L1 and L2, two transmission lines. So they have stated that the various parameters of the lines and generators are mentioned below. So G1 is your 250 MVA 15 kV and its positive sequence reactance is 0.25 on its own base. So this word is very important, huh? On its own base. And G2 100 MVA 15 kV positive sequence reactance of 10% on its own base. Now L1 and L2 is 10 km, the length of the transmission lines, and the positive sequence reactance of both of these transmission lines are 0.225 ohm per kilometer. They have told us to find out the three-phase fault at bus number 3 at here. So for your convenience, I have shown this diagram here. So xg1 would be the positive sequence reactance of generator 1, xg2 would be that of generator 2, and the xtl1 is the reactance of transmission line 1, and xtl2 is the reactance of transmission line 2. And we have a fault here since they clearly told that find the three-phase fault MVA at bus 3. So bus 3 was here. Therefore, we assume that there is a fault at this point. So this problem is also pretty simple. So first of all, we have to convert all the reactants to a particular base. So for that purpose, I have considered base MVA to be 250 and base kV to be 15 kilovolt. So the base reactance would be what, your V square by the power rating, right? So when we do it, we get it to be 0.9. Now ZB was calculated because your positive sequence reactance was given in ohms, right? So we have to convert it into per unit. So that is why I found out ZB. And again, XG2 was so its base was different, right? So it had to be converted into the base that we assume for this system, whole system. So when we do it, it comes out to be 0.25 per unit. Now your transmission line reactance would be this, right? So 0.225 the reactance in ohm divided by the base reactance, and this was in per kilometer, right? So you multiply into 10. So it comes out to be 2.5. Now we have to find out the fault level at this point, right? So this becomes kind of a parallel kind of a system, right? I'm talking about parallel system because you need to find out what would be the you have to find out the equivalent reactance of the system, right? Then you have to divide it by the voltage and find out what is the fault uh, current, and then multiply the voltage and current and find the fault MVA, right? So that is why you need to calculate the equivalent reactance. Hence, for this diagram, when we consider a fault here, this means that all these three reactances are in series. So combination of these three reactants, Xg1, XTL1, XTL2, would be in parallel with Xg2, right? So this is pretty simple, and I hope you understand. So yeah. So when we do this, so as I told, so this would be X equivalent of the system would be Xg1 plus XTL1 plus XTL2 in parallel to XG2. So when we do this, it comes out to be 0.2386 per unit, right? And the base voltage was considered to be 1 per unit. So yeah, so the the fault current at this point, the three-phase fault, right? So it is simple. So voltage divided by the reactance. So it comes out to be equivalent reactance, I mean to say, it comes out to be 4.19 per unit. And your fault MVA would be what? Voltage, base voltage, and the fault current, right? So 4.19 per unit. Now we have to find it in MVA, right? This is not in per unit. So our base MVA was, where is it? So 4.19 into 250, we get this around 1048 MG, which is your option number B. So this problem is also pretty simple, provided you realize the whole system that is given to you. You find out the base reactance of every component, and then sorry, not base reactance, the reactance in per unit for every component, and then draw the diagram and then see where the fault is occurring. So here, if the fault was in between, so if the fault was at bus 2, then these two components and these two components would have been in parallel, right? To an XTL2 in series, right? And their combination would be in parallel. So this is very simple to realize. This is only just the funda here in this kind of problem. You then find out the equivalent reactance, find out the fault current if that is what required to be found out, so that would be the answer. Otherwise, if they have asked to find out the fault MVA, so pretty simple, base voltage into fault current, that's it. And in this assignment you will see we are only looking at three-phase faults, since this assignment also has some problems on uh, s- positive, negative, and zero sequence components. So assignment 11, I guess, would be focused wholly on your faults in three-phase system. So there we'll get different kinds of faults that that occur in various power system components. So I hope this was clear. And if you have any doubt, I will be uploading the video in YouTube. You can comment there. I'll try to address whatever problems you have. Yeah. Okay. So let's see question number 9. So this is an example of sequence positive, negative, and sequence. Positive, negative, and zero sequence components का problem. So here they have told कि the line to ground voltage or the line to ground voltage on the high voltage side of a step up transformer are these, right? 100 kV, 33 kV, and 38 kV. So this is phase A, phase B, and phase C. They have mentioned also on phases A, B, and C respectively. The voltage of phase A leads that of phase B by 100 and lags that of phase C by 176.5 degrees. So when you see such a line, you see that every phase B and phase C is related with phase A. You immediately uh, consider phase A to be your base, right? So when you read this statement, you can write the different phase value. So which I have done here. As you can see, I have considered phase A to be my base, right? So I mean not base, it's a reference. It's a reference. So it is 100 at an angle of 0 kV. Now they are saying that phase A leads that of phase B by 100 degrees, or we can say that phase B lags phase A by 100 degrees. So therefore, phase B would be 33 at an angle of minus 100 kV, and phase A lags that of phase C by 176.5. Hence, phase C leads phase A by 176.5. So it is 38 at an angle of 176.5. Now they have told determine the magnitude of the negative sequence components of voltage. So this parameter lambda, as we know, we use this in sequence components problem. So as we know that lambda is 1 at an angle of 120 degree and lambda square is 1 at an angle of 240 degree. So they have told us determine the magnitude of the negative sequence component of voltage. So VA2 would be, as you know, the formula. So it is pretty well defined. You can check any textbook on, or you can also refer to the explanation videos of this course. So VA2 would be 1 by 3 into VA plus lambda square VB plus lambda VC. So in some books or in some other videos, you may see that this lambda is also treated as alpha, but they are the same, just different notations. Now we know the value of VA, which is 100. We know VB, we know VC, and we also know each of these components, right? And also be very careful while doing this calculation, because any sign change may lead to a wrong problem. I mean your option won't match with your answer, and you may end up losing time in the exam. So be very careful while solving each of these steps, because these are complex numbers, right? So yeah. So when you do this, it comes out to be 30.856 at an angle of minus 7.941 degrees. So they have told us to find out the magnitude, right? So magnitude is 30.856, which is between in this range, right? So it is the correct option is B. Pretty simple problem. Now here these are some symmetrical component operator problem. So some of these expressions are there, we need to find out which one is true, which one is false. Now I have done in a long way and in a process so that you are able to explain and do it on your own. So this may you may find these to be long, but it is for rather for a simpler explanation, which I thought to present you and give it to you, show it to you basically. Now this alpha, as we know, this is 1 at an angle of 120 degrees. So there are some properties basically. So alpha cube would be what? 1 at an angle of 360, right? So it would be 1 only. And alpha cube minus 1 is 0. And also alpha square plus alpha plus 1 is 0. And alpha to the power 4 is alpha. You can check this out. It is like this only. I mean, you will be able to prove each of the single properties also. So now let us look at the this thing. So alpha 28, alpha to the power 28 plus alpha to the power 326 equals to minus alpha 3. Sorry, alpha to the power 3. So let us consider the left hand side first. So now this alpha 28 to the power 28, we can write alpha to the power 4 whole 7, right? And also 326 can be written as alpha to the power 320 into alpha to the power 6. So as we know that your alpha to the power 4 is alpha to the power 1, right? So this becomes alpha 7 to the power 7. And also this 320 we can write it as alpha to the power 4 into 80. So again this becomes 1 here, right? So this becomes alpha to the power 80, and we can write alpha to the power 7 as alpha to the power 4 into alpha to the power 3, right? So again your, as we know, alpha cube is 1, so this becomes 1, and your alpha 4 is alpha, right? So this becomes alpha, this whole terms become alpha. Now as we did in the previous step, so we are replacing 80 by 4 into 20. So this alpha to the power 4 becomes 1, this becomes 20. We repeat this process again here. And yeah, so this is extended to the next page like this. You go down like this. So now this becomes alpha 11, right? So alpha 5 into alpha 6. So this becomes alpha 11. Now alpha 11 can be written as alpha 8 into alpha 3. So again alpha to the power 4 into 2, and alpha 3 is 1. So we get alpha, finally we get alpha plus alpha square. Now we had this property, right, that alpha square plus alpha plus 1 equals to 0. So we can write this as minus 1. On the right hand side we have minus alpha to the power 3, right? So as we know, alpha cube is 1, right? So it comes out to be minus 1, and hence we have here both the left hand side and right hand side are matching each other. Hence this is this comes out to be true. Yeah. Now let us look at the second statement here. So they are telling ki alpha plus 1 by alpha whole square, and the right hand term is alpha cube, right? So when we simplify this, it comes out to be this thing, right? Alpha to the power 4 plus 1 divided by alpha square plus 2. So yeah, so basically again your alpha 4 is alpha, right? And I am just multiplying this with this thing, so we get this. So this whole thing can be written like this, right? So I'm just breaking this alpha square into alpha square plus, I mean 2 alpha square into alpha square and alpha square. So this whole thing is 0, right? We saw alpha square plus alpha plus 1 is 0. So this term that you see here is 0. So we are left out with alpha square divided by alpha square, which is your 1, right? And again on the right hand side we have only alpha cube. We saw that it is 1 only. Therefore your left hand side and right hand side, they both match. Hence, this statement is true. Now let us look at the last one. So here let us look at the left hand side first. So alpha q plus alpha 4. Uh, okay, so yeah, I have done it like here. So uh, your alpha cube is 1 and alpha 4 is alpha, right? To the power 4 is alpha. And again, I am breaking this into alpha to the power 18 to alpha cube minus 1. So alpha 80 can be treated as alpha to the power 4 into 20. So this comes out to be this. Now again, you repeat the whole step here. You get 1 plus alpha divided by alpha to the power 5 minus 1. Again, you break this alpha to the power 4 into alpha minus 1, right? So this is again alpha, so you get alpha square minus 1. Now we have 1 plus alpha divided by 1 plus alpha into 1 alpha minus 1, right? So those two terms get cancelled and we are left out with 1 by 1 alpha minus 1. Now finally we have the this right hand side. So this is simplify these terms and finally you get this to be alpha by alpha minus 1. So here we see that our left hand side and right hand side, they don't match. Hence for this question only statement 1 and statement 2 are true. So which is your option number B. These are, I mean, these type of questions, if you get in exam, I should say that you try to solve this, because these are easy. Only thing is that it may take time if you try to solve this in these questions in this manner, but you will definitely fetch full marks in this kind of questions. Yeah. Okay, so let us go to problem number 11. Now here they have said that, yeah, now here they have said that a three-phase balanced star-connected voltage source in ACB sequence with frequency f hertz is connected to a star-connected balanced load with a purely balanced load which is purely capacitive. The instantaneous line currents and phase to neutral voltages are denoted as IA, IB, IC, and VN, VBN, VCN respectively, and their RMS values are denoted by this expression. We are told to find out what is the magnitude of R, right? So all of these are, first of all of these are your balance components, right? So we need to, I mean, since these are balance components, so this would be what if we consider phase A to be, reference, so or both for voltage and current, so this would be at an angle of 0. And again, in this way we write. So I mean, this kind of expressions, right? You have solved previously. So for three phase, phase B would be at an angle of 120 and phase C would be at an angle of 240, right? And so just here I am replacing this one at an angle of 120 by alpha, so this would be alpha square, right? So you just replace these components in these expressions and you get whole of this, right? So pretty simple problem this is. When you do this, when you solve this matrix, you see that all of these components are 0, which is, this all of these terms get cancelled out here. Therefore your the magnitude of R is your 0, which is your option number D. So this was a pretty simple problem. I hope this was clear. Yeah. Okay. Now let us look at question number 12. So a three-phase alternator generating unbalanced voltages is connected to an unbalanced load through a three-phase transmission line as shown in figure 12. The neutral of the alternator and the start point of the load are solidly grounded, as you see here and here. The phase voltages of the alternator are EA 15 at an angle of 0, EB 15 at an angle of minus 90, and EC 15 at an angle of 120, right? So clearly these are unbalanced components voltages, and they have also mentioned it. So the magnitude of the current flowing to the ground would be what? So this is pretty simple, right? You have the reactance of each phase, right? And you also have the voltage of each phase. Your ground current would be what? The sum of the current of each phases, right? So you calculate the current of each phase, right? You have the phase voltage and phase current, phase reactance of every phases. So you uh, calculate the phase current of every component. And mind you, just for a caution, here they have said that the phase voltages of the alternator, right? So that is why. So this is what phase voltage. So this is not line to line voltage, I mean to say. So you don't have to divide it by root 3 while finding out the phase current, right? So I mean that is why, I mean that was the point I wanted to mention. Therefore, your IA would be what? 7.5 at an angle of minus 90, IB is 5 at an angle of minus 180, and IC is 3.75 at an angle of 30 degrees. So ground current would be IA plus IB plus IC, and you calculate the sum. Do this operation, and you get this expression, right? So the magnitude, so they have told us to find out the magnitude of current. So this would be what? 5.89 amperes, which is your option number A. Again, pretty simple problem. Now, let us look at question number 3 and 3 and 4. Okay, and 6 also. So this would be our last three questions. Yeah. So two substations A and B are having individual short circuit capacities of 1500 MVA and 1200 MVA respectively. Both substations are operating at 11 kV. Now, substations A and B are interconnected by a cable having this much reactance per phase. Determine the short circuit capacity of station A after the interconnection. So this is the diagram, right? This is station 1, basically generator 1, generator 2. They are connected by this transmission line, and they have told us to determine the short circuit capacity of substation. So whenever you see this kind of line that determine the short circuit capacity of a component or of a substation, may like this. So you have to, assume that there is a three-phase fault. Basically, you have to short that component, and hence your circuit diagram would look something like this. Now, okay, so yeah, so this is the whole system that we have at our hands. Now, for solving the problem, what I have done, I have chosen a base of 1000 MVA and 11 kV. So you will see, so this is different from each of these base components, right? I mean, not base, generator components 1 and 2. Now, you may also solve this problem by considering G1 as the base or G2 as the base, but you will see that by considering this base, the calculations will get much simpler in terms of the values. So HG1 would be what? Your base Okay, so the okay, so we don't have XG1. Yeah. Okay, so XG1, sorry, XG1 would be what? Your VG1 square divided by 1500, and which is your 1000 divided by 1000. So here you see that the base voltage here is 11 kV. So VG1 is considered to be 1, right? Your base would be 1 base voltage, and your base MVA is 1000. So that is why I'm dividing 1500 divided by 1000, right? So when I do this, this comes out to be 2.3, sorry, 2 by 3 per unit. Now in the same way, so a transmission line reactance per phase was 0.242. So I calculate the reactance of transmission line in per unit, comes out to be 2 per unit. Now in this same way, I'm calculating the per unit reactance of generator 2, which comes out to be 5 by 6 per unit. So we now need to calculate the equivalent reactance. Now as you see that the fault was occurred at this point, right? So the reactance of this generator would be in parallel to the combination of the transmission line and generator 2 reactance, right? Pretty simple. We saw in one of the previous questions. So hence I have written this formula here to find the equivalent reactance. And when you do that, it comes out to be 0.541 per unit. So the base, so we have to find out what is the fault current at this point, right? So this would be what voltage divided by equivalent reactance. So it was 1, and this came out to be 0.541 per unit. So this is what 1.846 per unit, and hence your short circuit MVA would be what 1.846 into 1000 MVA. So it comes out to be around 1846 MVA, which doesn't match with any of these options. So your answer would be none of the above. Option number D. Okay. Now question 3 and 4 are connected. So here they have to asked us to determine the short circuit capacity of station B after interconnection. So station B basically means this generator 2 in our problem. So basically we have to assume that there is a three-phase fault here, and in the same way you, so here these two components would be in series, right? And these and the combination of these two would be in parallel as shown in this by this equation. So when you do this, so you calculate the equivalent reactance, and your ISC comes out to be 1.575. Yeah, okay. So your X equivalent comes out to be 0.633 per unit, and your ISC, or I mean fault current, short circuit level current, comes out to be 1.575 per unit. Therefore, your short circuit MVA is 1 into 1.575 into the base, right? So base was 1000 MVA. It comes out to be 1575 MVA, which is your option number C. So this was pretty simple problem. Now let's look at question number 6, which is the last question of assignment number 10 we will be looking at. So here, this is also a very simple problem. They have told a transformer is rated at 13.2 kV, 400 volt, 10 MVA, 20% reactance. Three such transformers are connected to the infinite bus. Determine the short circuit MVA of the transformers connected to the infinite bus. Okay, so here there are I have shown this diagram here. So there is a infinite bus here, and here there are three transformers connected. Now they are telling ki determine the short circuit MVA of the transformers connected to the infinite bus. So we have to, I mean, for this problem, we have to assume that there is a, a short circuit fault at the bus only, infinite bus only, right? Because we have to find out the total, combination of the transformers, the fault level by the combination of the transformers, right? Clearly, I mean, read this statement. Determine the short circuit MV of the transformers connected to the infinite bus. So basically, the short circuit MV of the infinite bus only. I mean, from the statement, this is what I understood. So, uh, so once you, I mean, understand what to find out, your problem is pretty simple. So xt1, I mean xt2 and xt3 is 0.2 per unit. So equivalent would be what? So since we have to find out a fault at this point, every component is connected in parallel, right? So this would be zero point 0.2 divided by 3. Your fault level or short circuit current would be what? Your voltage was 1, base voltage, and it comes out to be 15 per unit, and your base was 10, right? So it comes out to be 150 MVA, which is your option number D. So this was question number 6. Pretty simple problem this was, provided you know, I mean, you clearly read this statement. I hope this discussed today was were clear. Now again, as I told, I had to travel outside India, and I was out actually on 30th of September, last Friday. So that is why I had to reschedule this live session today. So this would be only for this week only. From next week onwards. So for assignment 11 and assignment 12, we will be meeting at Friday only from 7 to 8 p.m. And yeah, so that is it for this assignment number 10. I hope this was all of these problems were clear to you. I will be uploading the videos shortly, and also these materials. If you have any doubt, you can comment on the YouTube channel on this video in YouTube. I'll try to answer the doubt, clarify your doubts. Okay, then we'll then again meet next week, Friday, from 7 to 8 p.m. with assignment number 11. Thank you. Bye.